which is a battery. So which of these properties described are chemical properties? So I heard A, that's one. Wow. Jeez. So A is an answer. C is an answer as well, cooking an egg so it changes in color. And E, good. So A, C, and E are physical properties. B and D, these are physical properties. Okay, if anybody was tripped up on part C here, people always, every semester get confused on that. The trick here was changing in color, right? You think color is physical, but if you cook an egg, the reason it changes color is because you're denaturing those proteins, right? So that's a physical change. You can't uncook an egg, right? It's like not reversible, okay? So any questions on number one there? All right, cool. Number two, I'm asking which of the following is not a homogeneous mixture? So we have a bucket of seawater, blood, 5 liters of air, a cup of coffee, or steel. So what did we think was not homogeneous here? No, this one only has one correct answer. Not C. It's going to be B, blood. So blood is not homogeneous, right? So in terms of mixtures, right, what are the two types of mixtures we have? We have homogeneous, or you might say homogeneous, but someone told me that was the wrong pronunciation. Whatever. Homogeneous, we have heterogeneous as well. Right? So homogeneous or homogeneous means your mixture has the same composition throughout, right? Whereas a heterogeneous mixture does not have the same composition throughout, right? So why is blood heterogeneous? Sure, everybody here has gotten their blood drawn at some point, like at the doctor's office. Have you ever seen they put it in like that centrifuge and spin it around and it separates it into the layers? So blood is not homogeneous, it is heterogeneous. Okay. So any questions on number two for the different types of mixtures here? Okay. So now number three says to match the following SI unit prefix with its correct exponential value. So what I'm going to do is for each of these, we'll do like a big collective vote. So I'll go through the answers and just raise your hand if you chose that answer. So for Giga here, who chose A, B, C, D, E, some people say E, F, G, H. So the answer here, does anyone know what the correct answer is before I say it? F, good. So Giga is 10 to the negative 9, sorry, 10 to the positive 9. Okay. What about Millie? Is it A? Is it B? Is it C, D, E? Good, it should be E. So I saw a few hands go up for C, but Millie is 10 to the negative 3, right? It's negative 1,000. Right? We know milli is a small unit. Next for tera, is it A, B, C, D? Good. It's going to be D. So tera is 10 to the 12. Next, we have the unit prefix of kilo. So is it A, B, C? C, good. So kilo is positive 1,000, right? Not to be confused with milli. How about micro? Is it A, B, G, or H? Should be G, good. So micro is 10 to the negative 6, or in other words, negative a million. Okay. Hecto, is it A, B? It should be A, good. Hecto is 10 to the positive 2. And nano, is it B or H? B, good. Nano is 10 to the negative 9. That's negative a billion. And then mega, there's only one answer left. That's going to be H. So it's 10 to the positive 6. Okay, anybody have any questions on those? So if you don't have those memorized yet, please make sure you do, because you are going to need it when it comes to unit conversions and dimensional analysis. Okay, any questions on page 1 before we move on? Okay. Number 4 says your chemistry textbook weighs 2.8 pounds. Knowing that 2.2 pounds is equal to 1 kilogram, convert the weight from pounds into kilograms. So our book, we have 2.8 pounds, right? This is a simple dimensional analysis problem, right? I want to convert out of pounds and into kilograms. So what units are going to go on the numerator and denominator of this fraction here? So good, kilograms on top and pounds on the bottom, so it can cancel out, right? Then from there, we can just use our conversion factor, right? We know that 1 kilogram is 2.2 pounds. So what do you guys have as an answer for number 4? Good. We should have 1.27 kilograms. Okay, and I know I didn't follow sig figs, but sig figs at this point are out of the window because of in-person tests, which is a good thing. Okay. All right, number 5 here says, on a July day, temperatures in Death Valley, California can reach a sweltering 117 Fahrenheit or about 47 Celsius. Convert this to Kelvin. So what do we do in this problem? So you add 273 to what? The Fahrenheit or the Celsius? Celsius, right? I threw this in there to trick you and throw you off. We know Fahrenheit in science doesn't exist, right? It's just an American thing. So to go from Celsius to Kelvin, you just add 273. So 47 degrees Celsius plus 273 gets you what in Kelvin? Should be 320. Good. 320 Kelvin. Any questions so far? All right. Number 6, this one says, this is bad English. This should say weighs. An adult elephant weighs 400 centitons. Convert the weight into megatons. So we're going from centiton to megatons. So what can we start with in this problem? Just whatever we're given, right? So we have 400 centitons. And what did you guys do next? Yeah, good. So the roadmap here, right? I suggest you do not go straight from centitons to megatons. So what I suggest is go from centitons back to the base unit, which would be tons, and then up to megatons, because we know centi is small and mega is big, right? So in the middle is that base unit of tons. So we're going to go from centitons into tons. And we know the prefix centi is 10 to the negative 2, right? So 1 centiton has negative 100 tons. So now what unit am I in? I'm in tons, right? And can we get from tons into megatons? Yes, right? So who can remind me, what was the conversion between mega and the base unit? Good, 10 to the 6. So 1 megaton has 10 to the 6, or positive a million tons. And just as a reminder, when you're doing this in your calculator, right, all the numbers on the numerator you multiply, all the numbers on the denominator you divide. So what is this weight of this elephant in megatons? Okay, so it's a small number. Is there a better way we can express that number? 4 times 10 to the negative what? 6, good. And we need our unit, of course, which is megaton. Right? And then also these, right, the tons cancel off, and you just have megatons left. Okay, anybody have questions on that one? All right, number 7 says, which of the following is not an alkaline earth metal? Good, it should be D. Rubidium is not an alkaline earth metal. What is rubidium? So where do you find where do you find the alkaline earth metals on the periodic table? Group 2, right? Group 2, right? So group 1 is, what do we call these? So where rubidium is, right? What kind of a metal is it? It's an alkali metal, right? Group 2 here, this is the alkaline earth metals. So rubidium is the answer because this is an alkali metal. Okay. Next one here says calcium metal has a density of 1.54 grams per cubic centimeter. What is the volume of a 3.27 gram sample of this calcium metal? So what equation do we have to use here? Good. So density is equal to the mass divided by the volume. So we have density, we have mass, and we need to solve for the volume, right? So the density, 1.54, equals the mass over the volume. So the mass we have, 3.27, divided by my volume, which is going to be x. And how would you solve for x, which is on the denominator of this fraction here? Yeah, so essentially, we can cross multiply, right? So if you put the 1.54 over 1, and like the name implies, you cross multiply, 3.27 times 1 is just 3.27, equals 1.54 times x, which is 1.54x. All right, hopefully we're seeing the algebra from here. We just divide both sides by 1.54, so this cancels off. And what do you get x to be equal to? What's the volume here? 2.12, and what units? Good, it should be centimeters cubed, right? Because you get that from that unit of volume in the density value. Okay, any questions on that one there? or on page 2 before we move on. All right. All right, number 9 says a car is traveling at 72 miles per hour. How many feet per second is it moving? And here I give you the conversion factor that 1 mile has 5,280 feet. So the framework for this dimensional analysis problem is going from miles per hour into feet per second. Okay. So that means our miles have to get converted to feet, which is why I gave you that conversion, and then hours to seconds, which is a conversion you should be able to do on your own. So we're starting here with the 72 miles per hour. And we're going to deal with the unit on our numerator first. So let's convert from miles to feet. All right, so we know that 1 mile has 5,280 feet. So the miles cancel off. And up to this point in the problem, what unit is my number? Like if I were to solve right here, what unit would I be in? Feet per hour, right? But I want feet per second, right? So now we have to deal with this unit of hours, right? So for the hour to cancel out, where is this going to go on the fraction here? The top, right? And you know it has to go there because you want, in your final answer, right? You want the seconds on the bottom. So seconds can go down here. So obviously an hour is larger than a second, right? So how many seconds are in 1 hour? Good, 3,600. Right? Because in 1 hour, there's 60 minutes. 1 minute has 60 seconds. 60 times 60 is 3,600. So how many feet per second is my car traveling at here? Good. We have 105.6 feet per second. Okay, any questions on that problem, number 9? Okay. I'll give you guys a minute to do 10 and 11 if you haven't already, and then we'll discuss them in a couple of seconds. So 10 is asking to find the number of subatomic particles in the oxide ion, and 11 is asking to choose the list that only has one ionic compound. If anybody has come in late and did not sign in on the QR code, can you please just sign in on paper? So I just need your name and Z number. So I'll start around here and just, are you good? Are you good? Pass it around. All right, so for 10, what is the number of subatomic particles in the oxide ion? What do we think here? Good, C. Right, so remember we need subatomic particles. What are those? Those are protons, neutrons, and electrons, right? So protons, remember, is denoted by letter Z. Neutrons so electrons, I use the E minus, and then neutrons is just N. So Um, how did you determine that it had 8 protons? Yeah. Yeah, right. Remember, the atomic number of an element is how many protons it has, right? So oxygen is number 8. It means it has 8 protons. Now the electrons, right? This is a 2 minus ion. So if it was neutral, right? Obviously, protons are positive, electrons are negative. If it was neutral, they would be the same, right? But because it's 2 minus, we're going to have 2 extra electrons, right? So we're going to have a total of 10 electrons. And how about for the neutrons? How do you figure out the number of neutrons? Not necessarily, because you can figure it out from the data that's given. Yeah, sorry, I didn't see behind the screen. Yeah, so remember, the mass number of the elements, right? All these masses, right? Remember that mass number is equal to the protons plus the neutrons, right? So in the periodic table, if I have protons from the atomic number and I have the mass number, I can just subtract to figure out the neutrons, right? So the mass of oxygen is 16. It has 8 protons plus however many neutrons, right? So you just subtract 8 and you get 8 neutrons. Okay, do we all remember that? Any questions about that? Okay. Number 11 here, which of the following contains only one ionic compound? It's B, right? So remember, ionic compound is made up of a metal and a nonmetal. What's the other type of compound that we have? Covalent or molecular, right? And covalent or molecular compounds are made up of 2 or more nonmetals, right? So A, these are all covalent. B, these are also all covalent. C, um, these two are ionic. This is covalent, right? And then E, we have 2 ionic ones. We were only looking for 1 ionic. So B, water is covalent. Cesium oxide is ionic. And then the silver tetrachloride is covalent. I'm sorry, silicon tetrachloride. All right, any questions on that? Are we all good? All right. So now number 12, this says that chlorine has 2 stable isotopes. Cl35 is 75.8% abundant, and chlorine 37, which is 24.2% abundant. I'm asking you to calculate the average atomic mass for chlorine. So if you didn't do this one already, I'll give you a minute to think about it with the people around you. Remember, there's an equation you have to use for this. So take a minute to rekindle your memory, and then we'll go over it. Thank you. Anybody need this attendance over here? Can you guys just pass that back, please? All right. Are we good here? Does anybody have an answer for this problem? Good. You should get 35.48 about, just depending how you round. So how do we solve this for the average atomic mass? Remember, calculating average atomic mass is how all of these masses on the periodic table are calculated, right? You notice that pretty much none of them are whole numbers, right? They're all of these like weird decimals, right? The reason why we have all these odd decimals is because calculating average atomic mass, we're taking a weighted average of all of the isotopes for that element, right? So chlorine here, let's look at the equation for average atomic mass. So remember, it's the percent abundance divided by 100 times the mass for however many isotopes you have. So how many isotopes do we have in this problem? 2, right? So what we're going to do is percent abundance of the first one, so 75.8 divided by 100, right? So in other words, you're changing this percentage into a decimal, right? Times the mass. So what's the mass for, good, 35. So this is for isotope 1. Then we do it again for isotope 2. So we have 24.2 over 100 times 37. Right? Doing your calculator, add them up, and you should get, I'm going to write it down here because I'm running out of space, 35.48. And what units would go with that? Good. You can use AMU. That's terrible. That's an A. It's just not connecting. AMU, or you can just use U. All right. Any questions on number 12? All right. Number 13 here, this says that iodine is essential to your thyroid function and health. It's recommended that adults and teenagers consume 150 micrograms per day. How many iodine atoms are you consuming daily if you follow this guideline? So you guys have I'm sure you guys have heard of this. Like if you buy salt, it says like iodized salt. So they're adding iodine into it for your thyroid. So what are we doing? We're going from 150 micrograms into atoms, right? And something you should super definitely know is that this Greek letter mu, it kind of looks like a fancy script U. This means micro. Okay. So I'm giving the mass of iodine, and I want to convert it into atoms. So what's going to be like the framework or the blueprint to solving this problem here? Yeah. Good. So micrograms is not a good unit for us, right? We got to go convert this into grams. So that's a great place to start. So we know that a microgram is 10 to the negative 6 grams. So my unit of micrograms go away and I have grams. And let's be more specific. We're talking about iodine, right? So now if I'm in the grams of iodine, does this look more familiar now to get to atoms? Yeah, what are we thinking? Yeah. Good. So we have to go from grams to moles, right? And remember, we go from grams to moles by using the molar mass, right? So you just look on the periodic table what the mass of iodine is. So iodine has a molar mass of about 127. So now what unit are we in? We're in moles of iodine. Is there any way I can go from the moles to the atoms now? Good. We're going to use Avogadro's number. And what is Avogadro's number? Good. So remember, 1 mole of anything has Avogadro's number of particles, right? So you need to know that it's 6.022 times 10 to the 23 atoms. And remember Avogadro's number? I said you were going to memorize that like it was your phone number, right? So the moles cancel away and we're just left with the atoms. So if you follow this guideline of consuming 150 micrograms of iodine per day, how many iodine atoms are you putting into your body? Good. So I just didn't round. I have 7.11 times 10 to the 17 atoms of iodine. Right, and that makes sense that we get a humongous number because an atom is so tiny, right? Any questions on 13 or anything from page 3 before we flip to the next? Okay. Hopefully this one is very easy here. So for 14, I put arrows for each of these groups. So determine what the expected ion charge is. So what do we have for this arrow here? Good, +1. How about the group 2 here? +2. How about group 3 or group 13 here? This is +3. Remember, we skipped the group with carbon because it could be either +4 or -4, so you don't have to worry about knowing it. So that's good. Then we move into group 15 here with nitrogen. So what's this charge? Good, -3. Then what's next? -2. And then the halogens we know are -1. Right, so if any of these elements form ions, they're going to form an ion of that respective charge, right? Okay, good with that? All right, so using that rationale, number 15 says that aluminum and sulfate combine to form a compound. Determine the formula of this compound. So aluminum, of course, is element Al. And what ion charge does that make? Good. +3. And what about sulfate? What's the formula and charge of sulfate? Good. SO4, 2-. So remember, to make this compound, remember we do that drop and swap with the charges, right? So the 3 drops and swaps with the sulfate, and the 2 drops and swaps with the aluminum. So my chemical formula is going to be Al2, SO4, 3. Okay, any questions on that so far? So does anyone remember what was the purpose of doing that drop and swap? What does that do to this compound? Yeah.
It gets rid of like 2- and the +3 so that it
Yeah. Yeah, good. So it makes this electrically neutral, right? So if I were to take this and break it down, right? If I have, let's do this in black. I have 2 aluminums, right, which are 3 plus, right? So 2 times plus 3 is positive 6. If I break apart the sulfate, I have 3 sulfates, which are each a negative 2 charge. 3 times negative 2 is negative 6. Positive 6 plus negative 6, of course, that is 0. So it's electrically neutral, right? We have a net 0 charge. So that's the whole point of doing that drop and swap. All right, any questions on that? All right, number 16 says to name the following compounds. So give me a minute to write, and then we'll go through each of them, and you guys, excuse me, can just say them out. So compound 1, NaOH, what is this? Good, this is sodium hydroxide. And of course, we know that's one of the strong bases that we have to know and memorize, right? What about number 2, PbI2? What do we call that? Good, this is lead 2 iodide. Number 3, what do we call that? Good, this is oxalate. So one of those polyatomic ions you have to know. What's number 4, N2O? Good, so dinitrogen monoxide. Number 5, what do we call that? This is calcium oxide. And how about number 6? What's that? Good. This is going to be xenon hexafluoride. Yeah. So why is number 4 monoxide, but 5 is just oxide? What's the difference between 4 and 5? Covalent versus ionic, right? So when you're naming compounds, the first thing you have to ask yourself whether it is covalent or ionic. So remember, the covalent compounds, they require the numerical prefix to indicate how many atoms of that element it has, whereas ionic compounds, there's no numerical prefixes at all. Okay. Any questions with naming or the rules for naming? Okay. Yeah, sorry. For naming bases, it's just so like the really only ones you have to know are like the strong ones. So I have it in here. So we'll get to that in a little bit. And if I don't answer your question by then, just raise your hand again. All right. Next page here. So bisphenol A, which is C15H16O2, you've probably heard of, is known as BPA, and it's found in plastics, and it's a known neuroendocrine disruptor. So I want to know how many grams are in a 57.3 mole sample of BPA. So BPA, you guys probably see like the plastic like water bottles that says like BPA free or whatever, because that stuff is super bad for you. So what are we doing? We're going from the moles of BPA into the grams of BPA. This is mole. right? So this is just a mole to gram problem. So anybody that worked ahead, does anybody have the molar mass for BPA? Good, it's 228. Right, so the moles cancel off, and we're just left with grams of BPA. So what do you guys have as an answer here? Good, it's about 13,000, so 1.306 times 10 to the 4 grams of bisphenol A. Any questions with 17 there? All right. So now let's look at 18. I want to know, what is the percent composition of chlorine in COCl2? So this molecule is called phosgene. Phosgene. And it's a super poisonous gas. They used to use it in the First World War. So I'll give you a minute to think about it, remember the equation for this, and then we're going to go over it. All right, so what are we thinking here? What's the percent composition of chlorine in this phosgene molecule? Good, you should get 71%. So remember, the equation for percent composition is the number of atoms times the mass divided by the formula weight for the entire molecule, right? So, and then at the end times 100, right? So for percent composition, we're looking at chlorine here, right? So how many chlorine atoms do we have here? 2 times the mass of chlorine, which you can find in the periodic table, is 35.45, divided by the formula weight of the entire compound. So what's the molar mass for COCl2? 98.9. And to make it a percentage, you just multiply by 100 at the end. So you do 2 times 35.45 divided by 98.9 times 100, you'll get 71%. So really what this means is that this compound is about 71% of its mass is from the chlorine alone. That's really what this is telling us. Okay, any questions on that one? Okay. All right, who remembers how to do empirical and molecular formulas? Everyone's favorite. So number 19, this says an unknown substance is analyzed and it's found to contain 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen. There should be a percent here, but you get the idea. Then from mass spectrometry, the molar mass was determined to be 92 grams per mole. Determine the empirical formula and the molecular formula for this unknown substance. So To do this, we have to first figure out the empirical formula, and then from there we can convert it to the molecular formula. So in writing empirical formulas, does anyone remember the first thing that you assume about your sample? You assume it's 100 grams, right? So by assuming it's 100 grams, what can we do with these percentages here? We can just write them as grams, right? So we have 52.14 grams of carbon, 13.13 of H, and then 34.73 grams of oxygen. Okay, so we assume a 100-gram sample, we write the percentages as masses, and what comes after that? Good, so we divide by the molar mass, so we're converting everything into moles, right? So we'll do that here. Just converting everything into moles. Right, so grams to moles, not too bad. Now, what do we do next? Good, so you're gonna divide everything by the smallest number that you have. So of course here, 2.17 is the smallest number. So we're gonna divide everything by 2.17. Okay, when you do that, that's gonna give you the simplest ratio of atoms, right? Remember, an empirical formula is the simplest ratio of all the atoms, whereas the molecular formula is like the real composition of that compound, right? So from dividing these, it's going to give us the simplest ratio of atoms. So 4.34 divided by 2.17 is 2 for carbon. 13.13 over 2.17 is 6.05, which is close enough to 6. And then 2.17 divided by itself, of course, is just 1. So let's write it up here. What is my empirical formula? C2H6O, right? Are we done here? No, because now we have to figure out the molecular formula. So you always have to figure out the empirical first, and then from there you can get to the molecular. So remember, to get to the molecular formula, you have to do the molar mass, which I gave you, divided by the molar mass for the empirical formula. So we'll call that the empirical mass. Almost wrote empirical mass, right? So what's the molar mass here? 92 divided by the empirical mass, which you can figure out, right? So 12 times 2 plus 6 plus 16, that'll get you 46, right? Once you do that division, right, this 92 divided by 46 is 2. Whatever quotient you get, you are going to multiply to every term of the empirical formula to get your molecular formula, right? So we're going to do this entire thing times 2. So what's our molecular formula? It's going to be C4H12O2. Yeah. Molar mass of the empirical formula. So 24 plus 6 plus 16. 92. Okay. Any questions on that? Everybody good with that? Empirical molecular formulas? Am I good to erase here? Okay. All right, number 20, which of the following contain only strong acids? So I'll give you a moment to go through that list. All right, what do we think? What here only has strong acids? What's the answer choice here? It's not the good, it's going to be D. All right, so remember there are 7 strong acids and I think it's 5 strong bases you must know. So I'll write these up here. Does anybody remember the acronym I taught you for the strong acids? Yeah, so we can use let me can everybody see this board here? Yeah. So I'm gonna write the 7 strong acids out first, and then this sucks. So what you can remember for this is you can say, so I brought no clean cloth clothes. And the order in which I wrote those acids follows this acronym. So I brought no. Right. So what are the we have 7 strong acids. We have sulfuric acid. So just so you guys know, you need to memorize all of the 7 strong acids. So you need to know the name as well as the formula of it, right? So we have sulfuric acid, hydroiodic acid, hydrobromic acid, nitric acid, hydrochloric acid, which is our stomach acid. Then we have chloric acid and perchloric acid, right? So it kind of follows the anions follow that saying, right? So I brought no clean cloth clothes. All right. So those are the 7 strong acids you need to know. Now the strong bases you also have to know, and I thought I had something in there about that, but strong bases, remember the strong bases are a lot of the alkali and alkaline earth metals. And what polyatomic ion do the bases have? OH, which is hydroxide, right? So strong bases you need to know: lithium hydroxide, sodium hydroxide, potassium hydroxide. Then we have barium hydroxide, and then strontium hydroxide. So those are the bases you must, strong bases you must know. Okay, so we're talking about strong acids, strong bases. What makes an acid strong or a base strong? Does anyone remember that? So, okay, it does have to do with pH, but there's something else in the way it acts in solution. So it dissociates, but how does it dissociate? Getting there. So strong acids, strong bases will fully ionize into their ions, fully dissociate, right? Whereas anything that's weak, right, they're only going to partially dissociate. Okay? So make sure you do know that, all right? Any questions with strong acids, strong bases? Are we going to memorize those if we haven't already? Yes, we will. Awesome. All right, next page here. I'm asking you to balance the following equations. So I'll give you a minute to look at these and then we will balance these out. All right, so this first one here with boron trifluoride and lithium sulfite, what coefficients will balance this equation? Yeah, what do you have? Good, so 2, 3, and 6 with the lithium fluoride, right? If there's no number in front of the species, what is the coefficient there? It's a 1, good. All right. This next one here, this organic compound is nonane. It's a hydrocarbon that has 9 carbons. What kind of a reaction is this? Combustion, right? So what you need to know is for combustion, the reactants are a hydrocarbon and oxygen. And what are the products of combustion? Good, water and carbon dioxide. So how did you guys balance this one here? Good, so 14 in front of the oxygen. Good. And a 9. Good. Right, so you count them up and each element is equal on both sides of the equation, right? Okay, any questions on these two balancing here? All right, and then we have one more. How did you guys balance this equation here? So aluminum plus bromine gives you aluminum bromide. Good. So 2 with the aluminum, 3 with the bromine, and then a 2 with the aluminum bromide. Okay, any questions on balancing? Okay. Number 22 says, which of the following would precipitate in solution? So I believe on the back of on the last page, I included the solubility chart. So I'll give you guys a few minutes to look at this and determine what will precipitate. And there's 2 answers here. Okay. Anybody have an answer yet? We need more time. So if it's going to form a precipitate, right? What state of matter is that going to be? Solid, right? So in other words, I'm looking for which of these compounds is insoluble in aqueous solution. So any ideas on which would form a solid in a solution here? Not B. What do you, E? D? Yeah, D is an answer, and there's one more. C. Right, so this is really just looking at the chart and seeing what would be insoluble, right? And of course, you'll have the chart on your exam. So anybody have any questions on that for 22? Good. Okay. So now that we're on the idea of soluble versus insoluble, we need to do some precipitation reactions. So for the following reactions, write the net ionic equation showing all steps. So remember the 3 steps we have: balanced equation, complete ionic equation, and then the net ionic equation. Okay. So here I'm giving you the reactants of a problem, right? But I don't provide you the products. So how do we figure out the products, or how do we predict the products of these reactions? It's a metathesis reaction, right? Metathesis, double displacement, exchange, whatever you want to call it, right? So if you remember, I call this, it's an exchange reaction, right? So the cation from one is going to exchange and swap with the anion from the other. So I like to say that the outside goes with the outside, and then the inside with the inside. Right? So if so now, like, watch out, we're combining new things, right? So that means that we're putting together different charges, which means that we have to do the drop and swap of the charges again, right? So if I combine barium and sulfate, what is that formula going to be? So it's just going to be BaSO4, right? Because barium is +2, sulfate is -2. And combining sodium and chlorine, sodium is +1, chloride is -1, so it's just NaCl with 1-to-1 ratios. Okay. Next, what we have to do is predict the states of matter for the products, right? So here again, you'll consult your solubility table. You'll determine that barium sulfate is a solid, so it is insoluble, whereas sodium chloride is soluble, and that is aqueous, right? AQ. All right, what do we do next? Balance the equation, right? So you just need a 2 in front of the sodium chloride to balance that out. Right, so I'm going to just rewrite this with the balance equation step here. Right, so we have our balance equation. That's the first step. Then we have to write the complete ionic equation. So who remembers what you do to write a complete ionic equation? You break up all of the aqueous species, right? So you know you never break up solids or liquids. So the solid will not be ionized, right? So yeah, so you, right, you have to break into its ions. So with barium chloride, it's Ba2 plus, aqueous. And how do we write the chlorine there? 2Cl minus. So remember, when you have a subscript, it comes in front as a coefficient. Okay, I'm not going to write aqueous for all of them just to save time, but you know it should be there. So we broke this guy up, right? Now we move on to the sodium sulfate. So what is sodium sulfate going to look like ionized? 2Na plus, and then SO4, 2 minus. Right, so we ionize our reactants, we go to the products. What do I do with barium sulfate here? Nothing, right? Just write it exactly as it is. And then sodium chloride, how do we ionize this? Remember, this coefficient of 2, it multiplies to both, right? So we have 2Na plus and then 2Cl minus. Okay, what comes next now? This is the fun part. Now what did you say, Peter? Yeah, we can cancel the spectator ions, right? So the spectator ions are whatever shows up on both sides of the arrow here, right? So sodium and the chloride, see you later. And then finally, for the net ionic equation, we just write whatever was not crossed off, right? So what we have for the net ionic equation is barium 2 plus, aqueous, plus sulfate yields solid barium sulfate. Okay, any questions on writing that precipitation reaction? Yeah.
Like, great.
Yes, so any subscripts, right? It just goes in front as a coefficient. That's why we have the 2Cl and we have the 2Na. And also be careful. I don't have an example of it in the next one, but imagine you had both a subscript and a coefficient. Like imagine I had this, for example. What would this be? It would be 6Cl minus, right? So just make sure you look out for that if that pops up, okay? So let's do one more. This one I was a little bit meaner because I gave you only words. So I say calcium nitrate is mixed with sodium carbonate. So this is why all semester we have emphasized the importance of remembering your polyatomic ions, because if it's just given to you in a word, you have to know what that is. So calcium nitrate is CaNO3 2 with sodium carbonate, which is Na2CO3. So here are the reactants, right? Now, how are we forming the products? Again, it's metathesis, right? So we're going to do our cation anion swap. So now we're combining calcium with carbonate, which is calcium carbonate. And then sodium and nitrate is just, I'm running out of space. Sodium, gosh. Right. This equation needs to be balanced, so we put a 2 here. And looking at the solubility chart, does anybody know what the solid is going to be here? Yeah, calcium carbonate is insoluble. So this is solid. Sodium nitrate is aqueous. All right, so that's our first step of balanced equation, and then we proceed with the rest of it, right? So complete ionic equation. What does this look like? We're going to have calcium 2 plus 2 NO3 minus plus 2 Na plus, right? So we did that one. Now we move to the next one. Plus CO3 2 minus. Go to the products. Again, we have a solid, so we don't do anything there. Keep that guy together. And then sodium nitrate, 2 Na plus and 2 NO3, geez, 2 NO3 minus. Okay, everybody good so far? Okay, so now we can go ahead and cancel our spectators. So what's a spectator? It's going to be sodium and nitrate. So we're resulted with calcium 2 plus with carbonate, giving you solid calcium carbonate. All right, any questions on precipitation reactions? Okay, moving on to the next page here. So 24 says, determine which species are oxidized, reduced, and which species operate as the oxidizing and reducing agents. So first of all, what's this polyatomic here? So this is the dichromate ion, right? And it's reacting with iron here. So when it comes to doing these redox reactions, right? First, what you have to do is assign the oxidation number to all of the elements in these compounds, right? So make sure we memorize our oxidation state rules, right? So let's look at the dichromate first, right? Do we know the oxidation number of oxygen? So we do know the oxidation number of that, right? Because it's in our rules, right? Do we know the oxidation number of chromium? No. But do we know what the overall oxidation numbers has to equal to? -2, right? Because you know your sum of oxidation numbers equals the overall charge. So for this one, we know what oxygen is. We have to do some math to figure out what chromium is. So again, I'm looking at the oxidation number of each chromium individually. So we have 2 chromiums, right? So we can write that as 2x plus oxygen now. So what's the oxidation number for oxygen? -2. And how many oxygens do we have? Good. So 2x plus -2 times 7, that's -14, right? So I'm going to just rewrite that so it's not as messy. And again, what is this going to be equal to? -2. All right, so we do some simple algebra to solve for x here, right? You can move your 14 to the other side. 2x is equal to +12. So what's x going to be equal to? +6, right? So chromium is +6. Oxygen is -2. And that's good. Okay, now the rest of them are much easier because remember, when you have a monatomic ion, the oxidation number is just the charge of that ion. So for iron 2 plus, what can you guess is the oxidation number for that? 2 plus. Chromium 3 plus, this is 3 plus, and then iron is going to be 3 plus. Okay. So now we can compare both sides to determine what's being oxidized, what's being reduced, right? So remember, the importance of these redox reactions is that we are transferring electrons, right? So we're, remember when we learned oil rig, right? So remember that oxidation is the loss of electrons and reduction is the gain of electrons, right? So let's go and compare these now. So let's start with the chromium, right? Chromium goes from +6 to +3, right? So is that getting more positive or more negative? More negative, right? If it's getting more negative, is it gaining electrons or is it losing electrons? It's gaining electrons, right? So what do we call the gain of electrons? Reduction, right? So the dichromate is reduced. And because it's reduced, what does that have to make it as well? It's the, what's that specific word? Agent. It's the oxidizing agent. And I'll explain that more once we finish this. Okay, next we look at iron, right? Iron goes from 2 plus to 3 plus. Is that more positive or is that more negative? More positive. So if it's getting more positive, are we gaining electrons or losing electrons? We're losing electrons, right? So what do we call the loss of electrons from oil rig? That's oxidation, right? So iron is oxidized, and in turn, that'll make it the reducing agent. All right, so I know the agent part could be a little bit confusing because it's flip-flopped, but it actually makes sense why it is flip-flopped that way, right? So think, let's use the dichromate first, right? It was reduced, right? So it gained electrons, right? Now, these redox reactions, remember, it's happening by the transfer of electrons. So because dichromate was reduced, because it gained electrons, right? Like those electrons are not just like chilling out in free air, right? It's coming from somewhere. So because dichromate was reduced, it's the oxidizing agent because it calls for the iron to become oxidized. The dichromate is stealing the electrons from this iron here. Now, iron is oxidized and it's the reducing agent because it calls for something else to become reduced, right? Iron lost an electron, and that electron cannot just hang out in free space, right? It's got to go somewhere, it's got to do something. So because it lost its electron, it went to the dichromate, causing for this to become reduced, right? So you see like that coupling relationship there, all right? Any questions on 24 there? And if you need to freshen up on your oxidation state rules, look back at the chapter 3 SI worksheet, which I wrote them all out for you. Okay. For 25, in the reaction below, which species is oxidized? So what do we think here? Anybody do this one beforehand? Yeah, it should be B. So K2S is oxidized, right? So we do the same thing. We have to assign the numbers everywhere. So K is +1 times 2. Sulfur is -2. H plus is proton is just +1. For the nitrate, you have to do some math to figure that out. So you do x plus -6 equals -1. So nitrogen is +5. The O is -2 times 3. K plus is just +1. And what's the oxidation number of sulfur here? 0, right? Remember, when you have a free element, the oxidation number is 0. Then we have NO, so N is +2, O is -2, and then for water, H is +1 times 2, and O is -2. So why is K2S oxidized? What happens to K2S? So we look here, right? Sorry, you compare it to the S, not to the K, right? You don't look at the K because it doesn't change, right? It's +1 here and it's +1 here. So you have to look at the sulfur. Sulfur goes from -2 to 0 here. So -2 to 0 is getting more positive, right? So it's losing electrons. That's why it's oxidized. Okay. Any questions on redox? Good. Okay. All right, so now let's get to some stoichiometry. So 26 says, for the combustion of ethane, which is this, C2H6, what mass of water is formed if 32 liters of oxygen gas are reacted with it? And here I give you the conversion that 22.4 liters are equal to 1 mole. Right, so what are we doing? We're going from the liters of oxygen to the mass of water. Right? So what can I start with here? So before we do that, we have to convert from liters into moles. So I have 32 liters of O2, and I need to convert that into moles. And here, of course, I give you the conversion factor that there, in 1 mole, there's 22.4 liters of gas. So 1 mole of oxygen specifically, right? So now that I'm in the moles of oxygen, right, I'm in the moles of oxygen, does this look familiar now to get to the mass of water from here? Yeah, good. So we got to do the mole ratio, right? So I cannot convert straight from the moles of oxygen to the grams of water, right? Because those units don't align. So what I have to do is, using the balanced equation and those stoichiometric coefficients, is go from the moles of oxygen to the moles of water, and then from there I can get to the mass of water, right? So what is my mole ratio going to be? Hey, we got a 6-7 ratio, right? So let's keep track of the units, right? Liters of oxygen go away. The moles of oxygen go away. Now I have moles of water. And we can definitely go from the moles of water to the grams of water using what? Molar mass, right? So at this point, the moles of water go away, and then we just have the grams of water left. So if 32 liters of oxygen are reacting, how much water are we making? What mass of water? Good. I'm going to write it down here because I'm running out of space. I probably just didn't round, but 22 grams of water. Right, and that's because the grams of water is the only thing left. Okay, any questions on that one? Everybody good with that? All right. All right, so 27, this says, how many moles of sodium hydroxide are produced when 13 moles of sodium are reacted? So I'm starting with the moles of sodium, right? And I want to convert that to the moles of sodium hydroxide. So remember, the only way we can do this jump, right? The only way we can interrelate these different quantities is through the unit of moles, right? Remember back when we were doing stoichiometry, I said that like moles is like the common language of chemistry, right? So the only way we can interrelate these quantities is through the unit of moles, right? So we would have to use here the mole ratio, right? So I want my moles of sodium to go away. I'm solving for the mole of NaOH. We have a 1-to-1 ratio, right? It's 2/2. So you're just going to get 13 moles of NaOH. Yeah.
Yeah.
So if it was a 2-to-1 ratio, so if there was nothing here and it was just like a 1, then you would get 26. Because then you're just doing 13 times 2, right? But because we have that 2, 13 times 2 is 26, divided by 2, you get back to 13. Make sense? Cool. Any other questions there for 27? Okay, next page. 28 says aspirin, which is known as acetylsalicylic acid, is commonly used to treat fever, pain, and inflammation. And it is produced from the reaction of salicylic acid with acetic anhydride. And here I provide you the equation for the synthesis of aspirin. So I'm sure everybody here has taken aspirin before. Have you guys ever heard of salicylic acid before? Like skincare, right? Put it on your face. It comes from the willow tree. Fun fact. So here's our reaction, right? We have salicylic acid plus acetic anhydride gives you aspirin, which is, what you're interested in, and then acetic acid is just a byproduct. So, and just as a disclaimer, this equation is already balanced. So I'm interested in the formation of aspirin. Suppose we mix 1,000 grams of salicylic acid with 1,000 grams of acetic anhydride. And I want to know about the following questions. So for part A, I want to know which reactant is limiting, which reactant is in excess. Part B, I ask you to identify the theoretical yield of the reaction. And then part C, I ask you to calculate percent yield. So let's start working through part A. Okay, this is a limiting reactant problem, right? So remember, the idea with limiting reactant is, in the real world, when you're doing chemistry, you don't just have infinite amounts of reagents, right? At some point, one thing is going to run out, and it's going to limit how much product you make. So what we have to do is we have to go from the mass of each of our reactants, convert it to the mass of our product, and then from there we can determine the limiting reactant and the excess reactant, okay? And also, just for like test purposes, remember that reactant and reagent are the same thing, okay? So we are doing it for both salicylic acid and acetic anhydride. So Here we'll do it for salicylic acid, and then we'll do it for acetic anhydride. All right, so in the problem, we are mixing 1,000. Oh, there's like a button on this thing I keep hitting. We have 1,000 or 10 to the 3 grams of salicylic acid, which is C7H6O3. And we have to convert that to the grams or to the mass of aspirin, right? So what should I do with this mass of salicylic acid here? Convert it to moles, good. So just for shortcut purposes, I'm going to just abbreviate it here with the SA for salicylic acid. So we need to find out the molar mass for salicylic acid, and that is 138 once you count it up. So my grams of salicylic acid cancel away, and I now have the moles of salicylic acid. Right, so now from the moles of salicylic acid, what can we do from there? Good, we can get to the moles of aspirin, right? So we're here, moles of salicylic acid. I want to go here to aspirin, and we can only do that by the mole ratio, right? So like I said, the equation was already balanced. So what's the mole ratio or the stoichiometric ratio? It's 1-to-1, right? So we have 1 mole of salicylic acid and 1 mole of aspirin. Right, so now my unit of moles, salicylic acid canceled away. I have the moles of aspirin. And what can we do now? We can get to the grams of aspirin now using the molar mass, right? So this is just now doing moles to grams. The molar mass of aspirin is 180 grams. That's disgusting. 180 grams of aspirin. Right? Our moles of aspirin go away, and we're just left with the grams or the mass of aspirin. So who has the mass of aspirin from the 1,000 grams of salicylic acid? Good. You get 1,304.34 grams of aspirin. Okay, so cool. That's my first reactant, but it's a limiting reactant problem, so we got to do it again for the other reactant, right? So we're going to do the same thing now for the acetic anhydride, right? So we are starting with 1,000 grams of acetic anhydride, which is C4H16O3. And same deal here, we're going to convert that to the moles. So 1 mole of AA, acetic anhydride, is 102 grams. My grams go away. I'm in the moles of acetic anhydride. And now, again, I'll use my mole ratio to get to the moles of aspirin. Right? Moles of acetic anhydride are gone. We're in the moles of aspirin, and now we can get to the grams of aspirin, again, by using molar mass, right? So who has the mass for aspirin here with the 1,000 grams of acetic anhydride? Good, I've got 1,764. I'm running out of space. 0.7 grams of aspirin. All right, so here's what we get. Now, what is my limiting reactant? Good. So salicylic acid is the limiting reactant, right? Why is it the limiting reactant? It results in the least amount of product formed, right? Of course, 1,300 is smaller than 1,700, right? So this is how much we'll actually make. We'll never get to this amount because the salicylic acid is going to run out first, right? Okay, everybody good so far with part A? All right. Part B, identify the theoretical yield for this reaction. What is my theoretical yield? Good. Remember, the theoretical yield is the maximum amount of mass that is allowed by the limiting reactant. So the theoretical yield is the 1,304.34 grams. And then finally for this problem, part C, this says in a pharmaceutical plant, the actual yield of aspirin is 1,102 grams. What is the percent yield? So remember, percent yield is actual divided by theoretical times 100. So the actual yield you're always going to be provided, and the theoretical yield you have to figure out through the stoichiometry. So here we have our actual yield divided by our theoretical yield, which was determined by the limiting reactant. And then to make it a percent, you just multiply by 100. Who knows what the percent yield is for this reaction here? Everybody have 87? I have 86. 86, am I just, okay, it could just be a rounding thing, but I've got 86%. Okay. So percent yield is, just a measure of like, in a way, it's like how good you are at your synthesis, right? Like an 86% yield is very good, right? If you got like a 20% yield, that's not so good because then you're probably spending more money on the reactants than you are selling the product. So, all right. 29, how many moles of potassium hydroxide are present in a 46.7 milliliter solution that is 1.2 molar? So what equation do you have to use here? So overall, we can use molarity is moles over liters, right? I have molarity. I can figure out the liters, and I can do some math to figure out the moles, right? So what's my concentration, the molarity? It's 1.2. The moles I'm solving for, so that's X. And you have to convert your milliliters into liters. So when you do that, it'll be 0.0467. All right. So from here, we just cross multiply to solve for X. So how many moles do we have here? Good. 0.056 moles of potassium hydroxide. Okay, any questions on 29 for molarity? All righty. think we're all going to get 100 on this test. We don't have many questions today. All right, for number 30 here, I'm asking what is the pH of a solution with a hydronium? Remind me, what do these brackets mean again? Concentration, right? So this is molarity. Make sure you know that. So what's the pH of a solution with a hydronium concentration of 6.8 times 10 to the negative 3 molar? Good, it's going to be B, 2.17. So how do we find pH? Negative log of what? Of the hydronium concentration, right? Now, what if I had to do the opposite, right? Does anybody remember from high school math, logarithms, what the base of a logarithm is? It's a base 10, right? So if I need to do the opposite and go from pH to the hydronium concentration, remember you have to do 10 to the power of the negative pH. Right? So that 10 is essentially undoing that logarithm. All right, and actually the next one, I kind of just gave you the answer how to do that. For number 31, I say determine the hydronium ion concentration of an acid that has a pH of 3.8. So 10 to the negative 3.8. What do we have here as an answer? Good, 1.58 times 10 to the negative 4 molar. Okay. All right. This next one here, this says, suppose you are a chemistry lab TA. For a particular experiment with your students, you need 1.5 molar hydrochloric acid. The problem is you only have 6 molar, sorry, you have 3 liters of a 6 molar stock solution. So you have to dilute it to 1.5 molar. What is going to be the final volume of your diluted solution? So we have to use the dilution formula, which is M1 times V1 equals M2 times M2 times V2, right? So remember, the M1 V1 is your initial starting or stock, right? It's what you're starting with. Whereas M2 V2, that's your final set of parameters, right? So what's M1 and what's V1? Good. So M1 is 6 molar. V1 is 3 liters. What is M2? 1.5. And V2 is X, right? I'm solving for that. So just some simple math from here, right? 6 times 3 is 18 equals 1.5x. We're solving for x, you divide both sides by 1.5. And what is the final volume you get here? Good, 12 liters. All right. How are we doing so far? Still with me a little bit? Cool. All right. Moving on, the last page. All right. Number 33. So this says a 20 milliliter sample of a strong diprotic acid is titrated with 0.52 molar sodium hydroxide. After the procedure, it is found that 37.6 milliliters of the titrant sodium hydroxide was used. We need to figure out what is the concentration of the diprotic acid. All right, so this is a titration problem, okay? I know on the midterm, she did not give a titration problem, so I would strongly expect at least one titration problem in the final, okay? So just follow me carefully here because there's quite a bit of information you have to be able to extrapolate from this problem to be able to solve this, okay? So what do we think is the first thing that we're gonna need? So remember, titration we also call solution stoichiometry. So if we're doing stoichiometry, what is something that we're going to need? We need a balanced equation, right? So we have an acid with the base. Now, a diprotic acid, what does this mean? It has two hydrogens, right? Now, I don't know what the acid is, so the anion we're going to just write as X because we don't know what that is. So our diprotic acid is H2X. Okay. And it's reacted with the base, which is NaOH, right? And we have to figure out the products from here, right? So who can tell me what the products of this reaction are going to be? So we have water, right? Remember, the products of acid-base reactions are a water and a salt, right? So I'm going to just give it to you balanced already. We have 2H2O, right? And you can kind of get, in a way, these kind of do metathesis, right? H with OH, that's water. And then sodium with the X, what's that formula going to be? So Na, so this is going to be Na2X, right? And it's Na2 because if you look at the acid, right, if you do a reverse drop and swap, this unknown anion must be -2, right, if the hydrogen has 2. So this is -2, sodium is +1, right, so that 2 goes to here, okay? And then also we need another 2 to balance that right here. Okay. Let's just keep the colors consistent. Okay. So any questions on just writing that balanced equation so far? Okay, so we have a balanced equation. Now we can deal with the math or the stoichiometry, right? So I want to know the concentration of this acid, right? So what do I need to use? Molarity is moles divided by liters, right? So now let's look at the information that's provided for the acid and for the base. For the acid, all we have is the volume, right? For the base, what do we have? We have concentration. We also have the volume. So what do we have more information for, the acid or for the base? The base, right? So what we can do is, right, we're using this equation, mole over liter. From the information that's provided for the base, we can solve for the moles of sodium hydroxide. Then using stoichiometry, we can get the moles of the acid, right? And then from there, once we have the moles of the acid, we can plug in to find out what the concentration is, okay? So let's look at our base here, right? So we have concentration of 0.52 molar NaOH, right? So remember, M is moles over liters. So do we have the moles for the NaOH? No, right? We have to figure that out. That's X mole. The volume we have, right? We can convert that to liters. So you divide by 1,000 and you'll get 0.0376 liters. From here, we can figure out the moles, right? We just cross multiply. So X is equal to 0.0195 moles of NaOH. Okay, good so far. Any questions yet? All right, so I have my moles of sodium hydroxide. Now from here, am I able to figure out the moles of the acid? Yes, right, I can just use my mole ratio. So once I get the mole of my acid, I can figure out the concentration because we have the volume, right? So if I have 0.0195 moles of sodium hydroxide, I want to figure out the moles of this acid. So what is my mole ratio here? One to two, right? So from this, we determine that we have 0.00975 moles of the acid H2X, right? From there, I have the moles of the acid, I have the volume of the acid, and we can figure out what the concentration is going to be. So did anybody figure this out? The answer here is A, right? So you end up doing, I'm going to erase this part here. So, gosh, the answer is A. So for the acid, we have the moles and we have the volume, which was provided in the problem, right? So for the acid concentration, the molarity is equal to 0.00975 moles divided by 0.02 liters. And from there, you're going to get 0.487 molar H2X. So that is why our answer is A. Okay. Any questions on that? I know it was a lot of steps, but just, look at it. You see what information you have, what you have the most, what am I saying? Well, you have the most information to work with, and then you can kind of work your way around there. All right. One last problem before we all get out of here. And this one is a quick one. Number 34, true or false, ionic compounds dissociate and act as electrolytes in solution. What do we think? True, good. All right, so before anyone goes, part 2 is tomorrow at 3 o'clock in here. All right, if anybody did not sign in, please do that on your way out on this paper. All right, so yeah, that's all. Have a good night, and I'll see you guys tomorrow.